Welcome to Variational Principles and Lagrange's equations. Today we are going to discuss the energy function and the conservation of energy. We will begin by considering a general Lagrangian, L depending on Q, the derivative of Q with respect to time and time itself, with an explicit time dependence due to time-dependent constraints or time variation of the external potential. In that case, the total derivative of the Lagrangian with respect to time is given by the expression here. So by using the chain rule and the rules of partial differentiation, we have a sum over all of the generalized coordinates of the partial derivatives of L with respect to the generalized velocities, and this is multiplied by the generalized acceleration. The second term will be a similar sum containing the partial derivatives of L with respect to the generalized coordinates multiplied by the generalized velocities. And finally, the partial derivative of L with respect to time, which contains, if present, the explicit time dependence of L. Now, from the Lagrange equation, we know that this equality is true. And if we put the two together, what we obtain immediately is this is largely the same result, but we've just replaced these derivatives with the ones given here. And the reason why we do this is because then by writing things in this way, we can take the first two terms of the sum and write them down as a single sum over the derivative of the product here. And if that is the case, then by simply moving this whole term to the left-hand side, or equivalently, we can move this to the right-hand side and move this partial derivative to the left, or however you want to look at it. What you obtain is that the total time derivative of the quantity here plus this partial derivative is equal to 0. And the quantity in question here is called the energy function and is denoted by the letter h. So this is a function of generalized coordinates, generalized velocities, and possibly time, and it is given by the expression here. And the result that we have obtained, which is sometimes known as Jacobi's integral, is that the total time derivative of this energy function h is equal to minus the partial derivative of L with respect to time. From the equation 1.73, we know that generally the kinetic energy has a structure containing three terms. T0 is just a coordinate function, T1 is a linear function in velocities, and T2 is quadratic in velocities. Now, as it happens, usually the Lagrangian itself is a similar function structured as a sum of three terms, L0, L1, and L2, where L0 is a coordinate function, L1 is a homogeneous function of the generalized velocities, and to the first degree, and L2 is a homogeneous function of the generalized velocities to the second degree. That is, by being homogeneous functions in generalized velocities, it means that if we scale all of the velocities with a given factor, then the function itself scales with a power of that factor, the power being the degree of homogeneity. There is no intrinsic reason to classical mechanics imposing this structure of the Lagrangian, but nevertheless the result remains true for most problems of interest, namely problems involving position-dependent potentials or charged particles moving in electromagnetic fields. Then a result known in mathematics as Euler's theorem for a function f that is homogeneous of degree n in the variables xi states that a sum over the variables I of these products, so xi multiplying the partial derivative of f with respect to xi is simply the product n times f, where n is the degree of homogeneity of the function f. And then what follows from equation 2.53 is that, so from the definition of h, it follows that h is if we evaluate the expression here using the Euler's theorem, it follows that h is simply given by L2 minus L0. If the transformation equations 1.38 do not involve time explicitly, then it follows that t is equal with t2, and we remember this because both of these other terms involve the partial derivatives with respect to time. And for position-dependent potentials, we also know that L2 is going to be equal with T2, and L0 is going to be equal with minus V. And as such, H is going to be equal with L2 is just T2, so it's simply T, the kinetic energy, and minus L0 is simply V, so the potential energy. And as such, in this particular case, H is equal to E, and in particular, E is constant, where E is the total energy of the system. The conservation of H has distinct conditions from those identifying H with the total energy E. H can be conserved but different from the total energy, or it can be equal to the total energy but not be conserved. While L equals T minus U, regardless of choice for generalized coordinates, so I've written it here in a general case where I'm assuming that U can be a generalized potential depending both on coordinates and velocities. H depends on the choice of coordinates, both in magnitude and functional form. Therefore, various energy functions H can be generated for a given system based on different choices for generalized coordinates. Commonly in classical mechanics, the kinetic energy is a function of the squares of the generalized velocities or the squares of the conjugate momenta, and the potential depends only on coordinates. In this case, H is the total energy and is a conserved quantity. Now, as an application, we can consider a system having a Lagrangian L prime, which is equal to a Lagrangian L, which is describing a very simple dynamics, let's say a particle moving in a central field which is conservative, but the particle is constrained to be moving on a surface that itself can be changing in time. And we add this constraint to the Lagrangian L prime by appending the equation of constraint, which is sigma of coordinates and time, multiplied by a coefficient, which is an undetermined Lagrange multiplier, which itself can be a function of time, since the surface can change in time. And given that the equation of constraint for the surface has the general expression here, it follows that if we take its total time derivative, which is the expression here, this thing has to be equal with 0. Now, we can take the total time derivative of L prime and expand it as is given here. This is all very straightforward, and we are making use of the fact that we know what L dot is. It's simply the whole quantity here. And since we know that this result holds, the total time derivative of the term here is simply this one. But in this case, if we apply the variational principle to L prime, so if we go all the way back to the action integral and apply a variation with respect to the generalized coordinates, then we find that the Lagrange equations, so the equations of motion are given by the expression here, so which involves both the derivatives of L and the derivative of the surface with respect to the generalized coordinates. And then the result here can be plugged into here, and we can, if we put everything together and apply the procedure that we just used to define H, and also make use of the of simple observations like this quantity summed and multiplied with the velocities here uh, is the partial derivative here multiplied with mu, for example, and so on. If we put all these things together in a very straightforward way, we obtain the result here. So on the left-hand side, we have the total derivative with respect to time of this quantity. This looks like a usual function h, but minus this extra term here. And on the right-hand side, we are left with the partial derivatives, which this is the partial derivative of L. This is the partial derivative which results from this identification here that we've discussed, and we have the additional term here. And then it is clear that if we look in this derivative, because mu dot is 0, so these two will cancel out. And since we know that L describes a conservative system which does not have a time-dependent potential or constraints applied to it, this also disappears, and then it means that the quantity here and for which we are taking the derivative is just the total energy of the system. And the conclusion is that in this case, the total derivative of E with respect to time is given by minus mu, the Lagrange multiplier, times the partial derivative of t with respect to sigma, which describes how the surface itself is moving in time. And hopefully this is a correct result. Another interesting problem is that of a point mass m that is constrained to move on a vertical massless hoop of radius a that rotates about the vertical with angular velocity omega. The question that we must answer is the following. Can the particle be at rest at a point different from the bottom of the hoop? So we write the Lagrangian in the usual polar coordinates by taking into consideration from the very beginning that the radius of the particle is constant, is simply the radius of the hoop, and taking into account that the motion of the particle around the symmetry axis is simply described by the rotation of the hoop with the angular velocity omega. So the kinetic energy will have the expression here, and the minus v is going to be given by the quantity here. And then if we calculate the equation of motion, we simply find the result here in a very straightforward manner. Now, if we apply the definition of the energy function and calculate it based on this expression of L, we find that the energy function has three terms. The first two that I've written here are just the T2, so the part of the kinetic energy which is homogeneous in the degree of freedom of the system, which is the angle with respect to the axis of rotation, the angle of the particle with respect to the axis of rotation. V is simply the quantity here, and the additional term which shows up in H is the centrifugal energy, and this is due to the fact that a constraint is present in the fact that the particle must rotate along with the hoop around the vertical. Now, clearly, because the Lagrangian does not depend explicitly on time, this quantity is conserved. So this quantity is constant in time, and therefore I can choose a particular value for it, which is, let's say, the initial value. So the value when the angular velocity of the particle is 0 and the angle described by the particle with the vertical is 0. So the particle is resting at the top of the hoop. And in that case, h is simply the quantity here. And since it is conserved, I can take the expression here and make it equal with the quantity here, and then I can move the potential energy to the right hand side. And if I do this, I end up with the result here, to which I apply the condition that I want the angular velocity to be equal to 0. And then by a very simple manipulation, we end up with the result here, and finally with the equation placed in a box. For this equation to hold, the ratio of g to the product between a and omega squared has to be less or equal to 1, which implies that omega squared must be greater or equal to g over a. So if the if the velocity of the hoop, so yeah, the angular velocity of the hoop as it rotates about the symmetry axis is greater or equal with g over a, then the particle can be at rest at a given point on the hoop, which is different from the bottom. And the critical value of omega for which this result holds specifically is just g over a, which you can recognize as this would be the square of the natural frequency of oscillations for the system. Consider now a carriage running along rails on a rigid beam. At one end, the carriage is attached to a spring of rest length r0 and spring constant capital K, having its other end fixed on the beam. On the carriage, another set of rails is perpendicular to the first one, and along it moves a particle of mass m held by a spring fixed to the beam, having the spring constant K and null rest length. The whole system rotates in the plane of motion with angular velocity omega about the point of attachment of the first spring. The length of the second spring is always small compared to r0. We need to answer the following questions. What is the energy of the system, and is it conserved? What is the Jacobi integral in the laboratory system, and is it conserved? What is the Jacobi integral in a system rotating with angular velocity omega? Is it conserved? What is the relationship between the two integrals? So if we take as the coordinates of the particle to be x and y, which are the laboratory coordinates, so these are the coordinates of a fixed set of axes with respect to which this whole system rotates, then we can write these in terms of the lengths of the two springs, which are r0 plus L1 for the first spring, where r0 is the rest length of the spring, and L2, which is the stretching of the second spring, assuming that it has 0 rest length, and the angle of the particle with respect to, let's say, the x-axis, which is just omega t. And in writing them this way, we are assuming that the second beam is rotated in counterclockwise with respect to the first beam by 90 degrees. And if we have these coordinates and we take their derivatives with respect to time, then the Lagrangian is a sum of 4 terms, which I have written in the following order. I have written T2, which is the part of the kinetic energy that is quadratic in the generalized velocities, and it happens to be a homogeneous function of the second degree in these generalized velocities. the second term is minus the potential, which is just the sum of the potential energies of the two springs. The third term is the one which is linear in the generalized velocities and happens to be a homogeneous function of first degree in the generalized velocities, and this is the Coriolis part of the kinetic energy. And the last term is the term in kinetic energy, which is simply a function of the generalized coordinates, and this is the centrifugal component of the energy. And therefore, the total energy written in the laboratory coordinates is the sum of these four terms. So the centrifugal kinetic energy, the Coriolis kinetic energy, the part of the kinetic energy which is quadratic in the generalized velocities, and the potential energy. If we apply the definition of H, we find out that the energy function is given by the expression here. So it's T2 plus V minus T0. And by using the value of E, we can write it as the total energy E minus T1 minus 2T0. Now, given that the Lagrangian does not depend on time explicitly, it follows that the total derivative of h with respect to time is 0, and the energy function is conserved. But since the energy function is conserved, it follows that the total energy is not conserved in the laboratory frame, and its variation in time is in fact given by the derivative of t1 plus twice the derivative of t0. So a first conclusion is that the total energy of this rotating system is not conserved in the laboratory frame of reference. We can now write we can take these two equations for the laboratory coordinates and invert them to express the stretchings of the two springs as functions of x and y. And by inverting them, we obtain the results here. So, and what these equations define is the rotating frame of reference. And if we construct the Lagrangian in the rotating frame, so if we take the derivatives with respect to time of these quantities, and we write the potential energy in terms of them and so on, we find that the Lagrangian in the rotating frame has formally the same structure, so it's the sum of free kinetic terms minus the potential term, where so T2 in the rotating frame is just the part of the kinetic energy which is quadratic in the generalized velocities, and in this case it is also a homogeneous function of the second degree. The T1 is the Coriolis term, which is linear in the generalized velocities and homogeneous to the first degree in them, and T0 is just the centrifugal term in the rotating frame. The novelty in this case is that if we write the potential energy, so the quantity here in terms of the x and y coordinates, it turns out that in the rotating frame, the potential is explicitly time dependent through the trigonometric functions involved. So the energy in the rotating frame is going to be the sum of T2 plus T1 plus T0, where all of these quantities are primed as to reflect that we are working in the rotating frame, plus a time-dependent potential V prime. Then by using, once again, the definition of the energy function, we can calculate the function H prime, which happens to be given by the expression here. But now, because there is an explicit time dependence in L prime, which is given by the expression here, so this is the partial derivative of L prime with respect to t, happens to be the quantity here, which you can see it looks like a kind of interaction term between the two springs, it follows that the energy function in the rotating frame is not conserved. And furthermore, this implies that neither is the total energy conserved in the rotating frame, and it is in fact given by the expression here. So it is the time derivative of h prime plus the derivative of these two of the Coriolis and centrifugal terms in the kinetic energy. Now, as we have seen, I believe here, yeah. So we can, if we want to, yeah. This is just this is the original result here. So we know that h prime is equal with the t2 plus v minus t0, everything written in the rotating frame. But we also know that the quadratic term of the kinetic energy in the rotating frame, so the one here, this is in fact given by t2 plus t1 plus t0 in the laboratory frame. The potentials, if we go from one pair of coordinates to the other, happen to be the same. So v in the rotating frame, if we go from the x and y coordinates, we go to the L1 and L2 expressions, is going to be equal with v, and the same for the centrifugal energy, which is the same both in the rotating and the laboratory frame. And therefore this means that we can write the energy function in the rotating frame, so h prime, in terms of laboratory quantities, which happens to be the result here. And we also know that the energy function in the laboratory frame itself is given by the quantities here. And therefore we can find the relation between the two functions as, for example, their difference, h prime minus h, in terms of laboratory quantities is just t0 plus t1. Now, knowing that h is conserved, if we take the time derivative of this relation, we obtain the result here. But we also know that the derivative of h prime with respect to time is in fact the term here. And we also know that the derivative with respect to time of the energy in the laboratory frame is this expression. So from all of these three results, we can write the time derivative of E as, let's say, the time derivative of the centrifugal energy in the laboratory frame plus this interaction term. And if we're interested in finding an expression in terms of laboratory quantities for the rotating frame as well, we can once again write the energy in the rotating frame as the sum here, and we once again we know that this result is true. We know that this result is true and that this result is true. And what is a bit more difficult to check, but hopefully it's correct, if you work things out, so the Coriolis term written in the rotating frame is minus t1 minus t0. So it's up to the sign, it's minus the sum between the Coriolis and centrifugal kinetic terms in the laboratory frame. So if you put these together, you can write the energy in the rotating frame as the sum of these quantities. And knowing that h in the laboratory frame is this expression, it follows immediately by taking the time derivative that the time derivative of the energy in the rotating frame is twice the time derivative of the centrifugal energy in the laboratory frame. Now, in the presence of dissipation, we know that the Lagrange equations contain an additional term as given by the derivatives of with respect to the generalized velocities of the Rayleigh dissipation function. And since we already know how the total time derivative of a general Lagrangian L looks like, then from these two equations, we obtain immediately the result here by using the same trick as previously. And we know that the first term is just the time derivative of the energy function, and the second term is just the partial derivative of L with respect to time. And the third term, uh, given the fact that Rayleigh's dissipation function is a homogeneous function of the second degree in the generalized velocities, then by Euler's theorem, this is just 2 times the dissipation function. So the time variation of the energy function in a system where dissipation is present is equal with the previous result. It's minus the partial derivative of L with respect to time, from which we also need to subtract twice the Rayleigh dissipation function. So if L does not depend explicitly on time, and if H is equal with the total energy E, then we obtain that the time derivative of E is minus 2 times Rayleigh dissipation function, which is the result we have obtained previously in less general circumstances. As a simple problem, consider a Lagrangian, which is essentially the Lagrangian of a simple harmonic oscillator, which is multiplied by an exponential having the argument gamma times t, where t is the time and gamma is a constant. So this Lagrangian is just the exponential e to the power gamma t multiplying t2 minus v. And it leads to the equation of motion uh, here, which is generally recognized as the uh, equation of motion of a harmonic oscillator undergoing dissipation. Now, if we calculate the energy function for the system, it turns out to be the quantity here. And because the Lagrangian has an explicit time dependence given by the value here, it follows that the energy function itself is not constant in time. In fact, its derivative with respect to time is given by the quantity here, so it's minus gamma times L. And since the total energy is equal to T2 plus V, then it follows immediately from these two results that the time derivative of E is equal with minus 2 times gamma times T2. And this is an example of a situation where dissipation has been introduced in the problem without relying explicitly on Rayleigh's dissipation function, but we would obtain this exact same result and the same equation of motion if we studied a simple harmonic oscillator experiencing the effects of the dissipation function given here. So f is kappa over 2 times the squared of the generalized velocity q dot, where kappa is equal with the product between m and gamma. Another way to look at the problem would be the following. We can undergo a point transformation defining the new variable s as e to the power gamma t over 2 times q. And obviously we can solve this for q, we can calculate its time derivative, and then we can, starting from the defining Lagrangian here, we can write a new Lagrangian where the explicit time dependence vanishes. But notice that this Lagrangian does no longer contain something which looks like just a quadratic term in the kinetic energy and the potential. It contains a more complicated expression of the potential energy, but not of the potential, of the kinetic energy, sorry. But if if we now calculate the equation of motion corresponding to this Lagrangian, we get something that formally looks like the equation of motion for a harmonic oscillator without a manifested dissipation. But we need to be very careful with the way this effective frequency is structured. So if we make the notations here, so k over m is omega 0 squared and gamma over 2 is omega 1, then notice that if omega 0 is greater than omega 1, this equation describes what is simple harmonic motion, but it's simple harmonic motion in the s variable, which has hidden the this exponential. If we were to then solve this for q, what we have is what we would obtain is harmonic motion exponentially decreasing in amplitude due to this exponential. At the same time, if omega 0 is equal to omega 1 or is smaller than omega 1, then what this equation describes is no longer oscillatory motion, but it's simply damped motion. So the energy of the system dissipates before it can undergo any kind of oscillation. And the point where omega 0 is equal to omega 1 is known as the point of critical damping. Now, if we calculate the energy function in the variable s, then we find that it's simply given by T2 plus V. And since the Lagrangian written in this representation does not depend explicitly on time, then this energy function is constant. However, notice that the kinetic energy is the total energy is not just the sum of kinetic plus potential energy, in the sense that it's a quadratic kinetic term plus potential. It contains both a linear term and velocities and a term depending only on the coordinate s. And as such, given the result here, if we take its time derivative, it turns out that the energy is not constant in this representation either, and its variation in time is equal with the variation of t1 plus the variation of t0. In conclusion, in this section we have defined the energy function, its relation to a system's energy, and conservation conditions for these quantities. The results have been illustrated in various simple applications for time-dependent and dissipative systems. In the following chapter, we will discuss the central force problem. And with all that being said, I am going to leave you with the words of Max Planck regarding the principle of least action. And I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.